Yeah, there's some serious stuff in here. Hey, Paul, good morning.
How's it going?
Going great. Come on, everyone.
Hey, how's it going?
Hey, nice seeing you.
Yeah, nice seeing you again. Hey.
So, as you recall, Jeff referred to Paul's lab here as CSI Fort Collins. We're able to just about investigate everything, anything when it comes to computers and electronics. And so, Paul.
Anything material.
This is Paul Mazurkowitz. Some of you met Paul last night at dinner. He's going to give you a tour and a pretty in-depth understanding of what we do from a material sciences point of view to really build, hopefully, the best workstations and best products for HP that we possibly can. So, Paul, all yours.
Thanks. So, like Terry said, my name's Paul. I'm the chief scientist here in the Materials Analysis Lab. So my job is to help the engineers figure out complex problems that they have during development, and also I do help with customer support too if there are issues out in the field. So I think the easiest way to kind of show you what I do here is I'll take you through the lab and I'll show you a couple of the different tools that we have and how we actually use them. So why don't you all come in here into the first room. Getting a little toasty in here from having everything on, but the first thing I'm going to show you here is a real-time X-ray machine. So this tool is very similar to what you find in a dentist or a doctor's office or airport security, which many of you probably already went through recently. And the idea is to be able to look through things very quickly and easily. But this tool is a little different in that it is specifically made for the electronics industry. So we bought it from a company called X-Tech, and they've put in a bunch of artificial intelligence routines that allow us to, or to help us make decisions on the quality of things like solder joints and electrical connections. So I'm going to show you basically how the system works and how we use it for failure analysis. As kind of a fun example, you know, I've got an analog stopwatch here. These are really hard to find these days, but they do exist. And this is an example of something maybe somebody would bring in. It's not working anymore. You know, they can't wind it or whatever. You can see that opening this doesn't look very easy, and there is a chance that we would break it when we opened it, right? So it's always handy to be able to do non-destructive analysis where you can take a look at something without ripping into it. We'll go ahead and fire this up here, and I'll show you what's inside. The image will show up over here. So you can see we're looking at the bottom part of the watch that I have inside the box here right now. And when I move this around, you can see we can very, very quickly and easily scan over an area. And this is a video feed. It's not actually taking pictures, right? So we can zoom down here and actually see the inner workings of the watch. And you can see this one truly is analog, no batteries or circuit boards in this. And you can see the little gears moving everywhere. So if there was an issue where one of these cogs was out of place or there was a tooth broken off or something like that, we can really quickly and easily see that just that fast. You can see something banging back and forth here. Typically on something like an analog watch, your main failure mode here, we'll turn up the picture a bit, make it look a little prettier. You can see that, here's the spring, right, that you wind up to store the energy. If you overwind the spring, you'd expect it to snap somewhere. We can just go right to that area, check for that failure mode, and solve the problem that quick. And the idea is to be able to solve complex issues very, very quickly, but very, very accurately at the same time. Because when someone's having problems, it doesn't matter if it's, during development or out in the field, nobody wants to wait, right? We want to solve the problems as fast as we can. So I'll go ahead and show you one other thing here. This is a little more of a real-world example that I've got over here. This is a hard drive that we actually pulled out of a failed system. The system, actually, this is kind of interesting, the history of the system. This is something that was tested next door, and you saw that the dynamics testing where they beat everything up. Hopefully they broke something for you, I hope. Pieces flying off and everything.
Just got to drop something.
Oh, darn. So this came from there, and actually I had used this drive myself at my desk for a couple years after the test, just recycling the equipment we use over there. And I made a screeching noise one morning. My system rebooted, couldn't get it to start again, so I threw in a new hard drive and stuck this one in just to kind of see what was going on. So the first thing that I looked at is the microprocessor that's under here. So here's another hard drive. It's basically the controller chip on the hard drive that controls how it actually behaves. And if we look at the chip here with the X-ray, I can look right through this lid. So you can see these lids, they're thick plastic lids. This one has a metal covering over the top of it. I can go right through and look at a whole bunch of different features of this chip. As an example, if I get down here a little bit closer, I'm going to play with my image a little bit. For those of you into photography, I'm just in the histogram here, so we get a nice grayscale range. And And if you look, you can see all the different solder joints here. This is basically what holds the chip down right on the printed circuit assembly. They all look good. And then we're looking through the package here, and you can see these copper traces that go to little gold wires here. And then if we move over a little bit, we're actually looking at a shadow of the microchip right there. So you can't actually see silicon in an X-ray machine. It's not dense enough. But we can see the silver epoxy that they used to actually glue the chip down onto the surface. So that looks okay. You know, the wire bonds don't look broken. You know, if we were concerned about the wire bonds actually being broken, we could zoom in real close. The X-ray has a lot of magnification, right? We're not using light, so we can get up to thousands of X very quickly. But it's one thing that I noticed that was kind of interesting about this drive, and you know, one thing that we can investigate further is if you look here, these are little solder, like flat solder connections underneath the chip. And the idea behind them is to carry heat from the chip away from the chip, right? It's basically a heat sink on the underside of the chip. And you notice that these actually have big holes in them right here. So those are actually voids. Those are little air voids formed when we produce the equipment. And they could result in less heat going through here than was intended, right? So one of the reasons this drive may have failed could have had something to do with not enough heating in this particular area. That's one kind of thing. And the nice thing is, you know, I didn't have to take anything apart to see that, right? Just throw it in and away we go. And we'll go over here. The second thing that is a little unusual about this drive, if we back out, what we're looking at here, this is the platter of the drive right here, you know, that spins really fast that you write the data on. This arm right here floats across the surface and writes the data, and normally these park off the drive platter. In some, you know, in a lot of designs where they park away from it, so that when you move the drive around, you know, the head isn't bouncing on the surface and causing damage. But this one is awfully close to the spindle here, and you know, we can zoom in again. We can get a lot of magnification on this. What we're actually looking at right there, those are the individual heads of the hard drive right there. So each one of those is a tiny little electromagnet with a little bit of copper wrapped around it, and it pulses the magnetic energy onto the surface. This is awfully close to the spindle. There's a possibility that maybe the bearing wore out and the platter vibrated and knocked that head over to the side, right? Now it's stuck there. The screeching noise I heard may have been this actually running into there and, you know, going from 15,000 RPM to 0 in a second, right? That's going to make some noise. It could be by design, but again, we would usually have a schematic here with us that would tell us a lot about the equipment we were looking at. So again, this is kind of the first step in a failure analysis process where we go through and find out as much as we possibly can quickly and non-destructively and see if we can get to the problem that way. So I'm going to go ahead and turn this off. And by the way, if I mention anything you got a question on, just feel free to interrupt me. That's fine. So, so the next thing I'm going to show you is this electron microscope. I've got the picture up on the board because I wasn't sure how easy it would be for people to see. But it looks like we've got a small enough group. So I'll show you how this works. This is basically a microscope, so it's for looking at really small items. But the difference is we're using a high-energy electron beam instead of regular visible light to look at our sample. And why would you want to do that? What's wrong with visible light, right? Well, for those of you into photography, you know that there's this thing called depth of field, right? Whereas as you go higher and higher in magnification, your depth of field gets smaller and smaller, right? So by the time we get to, you know, 500x, you've just got this thin little layer that you can see, right? Well, with an electron microscope, because we're using such high energy light right here, X-rays, we actually get very three-dimensional images with very deep depth of field at very high mag. So you've seen, like on the news, you've seen pictures of like viruses and small bugs and things. Almost all of those are taken with an electron microscope. So why do we use one of those at HP? Well, as you can see, this is a current Intel chip here. You can see that some of the parts are getting really, really tiny on these things. I mean, small enough where they're hard to see, like the whole package is hard to see with the visible eye. So what I have here, just to kind of blow it up for everybody, this is this actual chip. I just took an optical picture of it so everybody can see. If any one of these capacitors cracks or breaks, this chip isn't going to work anymore, right? So we have to be able to find tiny little cracks, bits of contamination. You can see there's something there, right there on that capacitor. Maybe we want to know what that is, right, and figure it out. It might interfere, right? Or we could look for cracks or other problems that might be on this chip. So you need a tool like this that has a lot of depth of field to be able to screen over complex parts like this. So I threw something in the SEM just to kind of give you an idea of how it works here. I'll go ahead and turn it on here.
What are we looking at?
I'll show you. It's a secret until I pan out here. So, so you can see what we're looking at first. You know, we've got kind of a taffy-like appearance here.